I'll now look at using the power storage off-grid model for an example where grid electricity is available in both the base and the proposed case. This example might be of interest to somebody considering using photovoltaics in a location where net metering is not permitted, or due to some other consideration, it is not possible to feed surplus electricity onto the grid. The battery would ensure that the use of solar electricity is maximized. In RETScreen, this situation is best modeled as an off-grid system with grid acting as backup for those times when the combination of PV and battery is unable to satisfy the load. We'll look at this for a location in Alberta, which has net billing but not net metering. In Alberta, electricity fed onto the grid is not credited for transmission and distribution charges, which are significant. Consequently, there is a difference of at least 3 cents per kilowatt hour between electricity purchased from the grid and surplus PV output fed onto the grid. In the Virtual Energy Analyzer, I select Power, Storage, Off-Grid, set the type to photovoltaic, and then pick the archetype for a load of 24 kilowatt hours per day, met by the grid in the base case and PV plus battery plus grid in the proposed case. The 24 kilowatt hour per day load might be appropriate for a small business. I pick Medicine Hat as the location and hit Calculate. On the location worksheet, we find the climate data for Medicine Hat. Although it has perhaps the best annual solar resource in Canada, it is at 50 degrees north, so there is significant seasonal variability. The facility worksheet confirms that we are comparing PV plus battery plus grid in the proposed case to grid alone in the base case. On the energy worksheet, I might want to change the cost of electricity. I'll use 11 cents per kilowatt hour. This would be the tariff for purchasing electricity from the grid. The base case power system and load characteristics page confirms that in the base case we are using only grid electricity. There are no separate O&M costs associated with the grid connection, unlike in previous examples. The load is 24 kilowatt hours AC per day in both the base case and the proposed case. The intermittent resource load correlation is 0, corresponding to loads that are on during both day and night. We might raise the peak load to 10 kilowatts for a small business. Then we'd also increase the size of the inverter to be able to provide this. As shown in a previous video, the cost of the inverter is folded into the cost of the PV array, which we will talk about in a moment. The battery would likely be indoors, so I'll use constant temperature control with a temperature of 20 degrees Celsius. The archetype has sized the battery and PV array to ensure that they meet almost the entire load. This makes sense at off-grid sites, but it is unlikely to be financially optimal at on-grid sites, where using the grid from time to time is perfectly acceptable. I'll reduce the battery autonomy to 1 day, and therefore end up with a smaller battery of 60 kilowatt hours. I could adjust the cost per kilowatt hour, for example, using the cost database. Since 60 kilowatt hours is large enough to see volume discounts, I might look at the minimum end of the range. The current estimate of $295 per kilowatt hour is representative of sealed industrial gel or AGM batteries. I'd likely pay more for lithium-ion batteries, but achieve a much better cycle lifetime. These choices of technology would not require regular maintenance. If I were willing to do regular maintenance, like adding distilled water to the batteries, I could use cheaper vented batteries that still achieve a good lifetime. On the base load photovoltaic page, I see that the archetype has configured the fixed PV array due south at a slope equal to the latitude plus 15 degrees. This somewhat compensates for the much decreased solar availability during winter, because it collects more sunshine when the sun is near the horizon, as it is in winter. This could be a parameter needing optimization given the availability of grid backup. Even so, during the summer months, the current sizing is satisfying 100% of the load. There is likely significant surplus electricity being fed onto the grid. RETScreen does not currently attribute any value to that surplus, so for the simplest analysis, we can size the array to minimize the surplus. With an array of 7 kilowatts, there should not be a lot of surplus, even during summer. I can update the initial costs and O&M costs to account for the decline in cost since this cost data was valid. I'll use a factor of 0.75 as a user-defined adjustment. On the peak load grid electricity page, I'll set the charger efficiency to 0% since there is no need to charge the battery with grid electricity. The parameter has no influence currently, but this will avoid confusion. It is important to heed RETScreen's warning that the capacity of the grid connection, set by the archetype to the original peak load of 5 kilowatts, is insufficient for the updated peak of 10 kilowatts. I'll use 10 kilowatts, even though I know that the grid can supply much more than that. You'll note that this change does affect the electricity delivered to the load by the grid. The variable portion of the grid electricity costs will be about $116 per year. The fixed portion of the costs, that is, the daily charge just for having a grid connection, will be the same in both the base and proposed case, so doesn't enter the calculations of incremental costs. On the cost worksheet, I'll update the unit cost of PV to reflect the change I made to that value. The battery cost is fine for the initial costs, but we need to change it under the periodic costs, where it is the cost of the much larger battery initially proposed for the archetype. I'll copy the value from the initial costs. Also, since we are using a smaller battery, it will often cycle to a deeper depth of discharge and might only last 8 years. The emission worksheet shows that there are modest emissions reductions arising from this project, around 5 tons of CO2 equivalent annually. Looking at the finance worksheet, we can conclude that this is not a particularly attractive project. One might argue that this conclusion is due to our use of lead-acid batteries. Lithium-ion batteries have better performance. Based on the cost database, we can cycle them deeper and achieve a longer lifetime. They are also more efficient, and their costs are declining over time. I'll be optimistic and choose a low cost of $600 per kilowatt hour, a maximum depth of discharge of 100%, and an efficiency of 90%. On the cost worksheet, I'll further assume that the battery will last 20 years and that its cost in today's dollars will have fallen by half in that time. This does improve the project slightly, but it does not change our conclusion. We have not included all benefits of the proposed case system. For one, any sales of surplus electricity are ignored, but these should be small with the current array sizing. The purchaser might accord some benefit to GHG emissions reductions, even if they are difficult to monetize. Another benefit is that the system can serve as a very large uninterruptible power supply that might allow the business to operate even during extended grid outages. On the cost worksheet, I can enter a guess for what it is worth to the business on an annual basis. This does improve things, but it is still not a profitable project. If the UPS functionality is valued at $2,000 per year, however, this might start to make sense. Of course, we'd need to consider whether we could not provide this benefit in some other way, such as with a generator, and we'd need to go back and check our assumptions, particularly those optimistic ones related to the lithium-ion battery.